All right, welcome back. And in this second part, we will discuss the remaining part of section 3.4. And we will do 3.5, the Markov property, and also 3.6. So we essentially finish up chapter 3. And we will start with some informal but very useful notation. So let's see what we have seen so far. We have proved just at the end of the last lecture, we have proved that for the mesh size going to 0 from above, so Pn, the mesh of the partition Pn going to 0, the sum j runs from 0 to the number of points in this partition, mn minus 1, of the square increments is equal to t almost surely. That is what we have proved. And we can also write t as the integral from 0 to capital T of dt. Looks a bit awkward maybe, but in fact it is just the same. Now, if we look at this carefully, we can see here something like delta W, the increment in W square, because we have two of them. Yeah. And now if we look at that sum of delta W, that looks like a Riemann sum with delta W as the argument. Yeah, so that looks like a Riemann sum. And if we take that mesh size to 0, so if we make it smaller and smaller, we will turn the delta W into a dW. And that is how we get to our informal notation. Yeah. So the above with the mesh width going to 0 is then the notation used is as follows. We say dW is equal to dt. So we see this as dW is equal to dt. Make a square around it. And in a way, you can interpret this as the quadratic variation formula, but then in differential form. So in a sense, this stands for the integral between 0 and t of dWt. dWt is equal to the integral from 0 to t of dt. And actually, we will use this information, this informal notation, a lot in financial mathematics and also in computational finance in the master course. So this is really one of the basic ingredients, and especially also in chapter 4 when we do Ito calculus, and we will have stochastic integration with respect to a Brownian motion, and when we are dealing with function of a Brownian motion. We encounter dW a lot, often, and then we can easily replace it by dt. There is more. So there are more definitions that we can write down informally in an informal notation. And one of them is the definition of the cross variation. And later we will write that down informally as dW dt. dW dt. But for now, the cross variation, this is given again by the mesh of the partition going to 0 from above. Pn mesh goes to 0. And again, the sum j is 0 to the number of points in the partition. And now this is wtj plus 1 minus wtj multiplied by the size of the time step, tj plus 1 minus tj. So it is an increment in the Brownian motion multiplied by an increment in the time. Now, what can we do with that? Well, we can, again, remember the mesh goes to 0, and Brownian motion is a random variable, but with a fixed omega, with a fixed event. This is, in fact, a continuous path. Right? It's a continuous function for a fixed omega. When t is running and a fixed omega, this is a continuous function. And now we can replace, with the mesh going to 0, we can replace this by the largest element. And so that is the maximum for some k between 0 and the number of elements here. For some k, this term w Tj plus 1 minus Wtj is replaced by the maximum over all these elements of Wtk plus 1 minus Wtk. Yeah, so we replace it by the maximum. It's equal because the mesh width is going to 0. Now this is then not depending on j anymore, so we can take it out of the sum operator. Yeah, so it's in limit, the limit mesh going to 0 of that maximum of Wt k plus 1 minus Wtk times the sum, j runs from 0 to the number of points in the partition of Tj plus 1 minus Tj. Well, this part here, that is equal to capital T. And because this is a continuous process, and because the mesh is going to 0, then this will eventually go to 0. This will go to 0 when the mesh size, when the time step is getting smaller and smaller. This will eventually go to 0 in a continuous process. And all in all, this, as a result, this is equal to 0. And again, we see here a delta W, and here we see a delta T. And for time step going to 0, we can write this as shorthand in a shorthand notation as dw dt is equal to 0. And this is another important quantity that we will be using in chapter 4. And the third one, that is just the quadratic variation of t. So f function, just a function of t being t. And we know that, of course, the function t is continuously differentiable, a continuously differentiable function. And we have already discussed in the previous lecture that the quadratic variation of a continuously differentiable function is equal to 0. So that is this. That is what we have shown in the previous lecture. And now in the informal notation, we write this like this. dt is equal to 0. Yeah. So in a way, you can see this also as higher order terms turning to 0. dt is equal to 0. It goes quadratically to 0. Yeah, this is just the informal notation. So what have we seen in terms of the informal notation? Well, first of all, we had the cross variation. The cross variation officially defined as follows, and we write it like dw dt or dwt dt, yeah, and that is equal to 0. Then we had the quadratic variation, dt dt, denoted by this, always with the mesh width going to 0. Therefore, we get to these tiny increments, and the informal notation tells us that in quadratic variation of Brownian motion tells us dw is dt. Then the cross variation dw dt is equal to 0. And then the quadratic variation of time just dt is equal to 0. And again, this will show to be very useful when we do Ito calculus. We can just simply make use of this. Now, a final thing that we would like to tell you, and that for which we will give an example later on, is that quadratic variation is the source of volatility in stock price processes that are driven by a Brownian motion. And we will show that now in an example, but we will come back to that later again in chapter 4. But for now, we will do an example with this. Okay, let's see an example of quadratic variation in practice. And the example is an important one. It deals with volatility of a geometric Brownian motion. And a geometric Brownian motion is one of the models that is typically used in financial mathematics to model stock prices, or more generally to model asset prices. It is a basic model but still it is a stepping stone towards more difficult models. And it is the fundamental model for a famous theory, the Black-Scholes-Merton option pricing theory. So we will see that quadratic variation is connected to estimating the volatility of a geometric Brownian motion. So let alpha be a constant in R, and let sigma be a positive parameter. And alpha will be connected to the growth rate, the drift, the growth rate of a stock price. And sigma will be connected to the volatility, the uncertainty in the stock prices. Now the geometric Brownian motion, which we abbreviate by GBM, is defined as follows. It is a process S from stock price, a process of T, and time T runs from 0 to capital T, where capital T would be, say, the final time of an option contract. But we're dealing with the stock itself, right? Not the option, we're dealing with the stock itself right now. Then the stock is defined as S of T is equal to some initial value S0 times the exponential function exponent sigma W plus alpha minus 1/2 sigma squared times T. So this is a basic model for a stock price, and the WT here in the exponent of the exponential function, that is a Brownian motion, T greater or equal to 0, that's a Brownian motion, and it is, added to that is this term, and it's multiplied by the sigma. At time 0, we have S0, and basically this is a model for the stock price in the future. Right? S0 is the stock price value now, and we look at the development in the future, which is then based on a Brownian motion in the exponent of this model. Now, if we look a bit more carefully to the exponent, sigma W plus alpha minus 1/2 sigma squared times T, if we look a bit more detail here, we recognize this is a Brownian motion and some deterministic term. And the expectation of the Brownian motion is 0, as we know. Then the expectation of this whole expression is equal to this deterministic shift, alpha minus 1/2 sigma squared T. So that is here. And a Brownian motion is normally distributed, and with the shift, it's a shifted Brownian motion. It's still normally distributed now with mean alpha minus 1/2 sigma squared times T. And the variance, of course, the variance of this deterministic term is equal to 0. And the variance of sigma times W is, the variance of a constant is the constant square. And the variance of WT is T, as we know. So then the variance of the complete expression of the complete exponent is sigma squared times T. And again, this process ST, T greater or equal to 0, that is called a geometric Brownian motion. And its value, again here listed on the slide, its value lies in the fact that this forms the basis for the Black-Scholes-Merton option pricing formula. So the option pricing formula by Black-Scholes and Merton is based on the assumption of a geometric Brownian motion for the underlying stock price. Scholes and Merton received the Nobel Prize for their option pricing formula in 1997, where Fisher-Black passed away already in 1995, so he couldn't get it anymore. An important thing, if you see this, is that stock price is larger or equal to 0. So exponential function is greater than 0. As 0, we assume it's also greater than 0. So we deal with positive stock prices. And of course, that is also what we see in practice. So that is one of the desired properties. And now this parameter sigma, that is called the volatility of the asset prices. It's something like the uncertainty in the asset prices. it's related to the zigzag curve that we often encounter if we look at stock prices. And the question could be, how can we estimate sigma? How can we estimate sigma from a specific price path? And this we will see will be related to the quadratic variation. And we look at that on a certain time interval from T1 to T2, capital T1 to capital T2. So let T1 be larger or equal to 0 and T2 be larger or equal to T1. Let them be given. And let's consider a time partition between T1 and T2. So T0, little t0 set equal to T1. And then we have a time partition T0, T1, T2, Tm minus 1 up to Tm, which is equal to T2. A partition in time, instances in time. Think of time points where we can observe the stock prices, for example. With the help of these time points, we can say something about the volatility. And for that, we use a well-known concept in finance, which is we look at so-called log returns. We look at the logarithm of the stock price at the new time point divided by the stock price at the old time point. So this we call log return. A return is something like new relative to old, so the new stock price relative to the old stock price. That can be seen as an approximation of a return or a specific kind of return. And with a logarithm, we call it the log return. And the log return. And we know from the rules from working with logarithms that the logarithm of this difference is the logarithm of sti plus 1 minus the logarithm of sti. You may know that still from high school. The logarithm of this division is log a minus log b. Log a over b is log a minus log b. Well, we were dealing with exponential functions. Let me look back a slide. We were dealing with exponential functions here. And so the log of the exponent, the log of the exponential function is the exponent, and the S0 will cancel out if we look at the relative distance as at ti plus 1 divided by sti. So what we get is the following. The logarithm of a over b is log a minus log b. And that is then the exponent, sigma, w at time ti plus 1 minus w at ti, plus this drift term, so this growth term, alpha minus 1/2 sigma square ti plus 1 minus ti. And now this realized volatility that we try to estimate, so we could try to estimate from an historical path, what is the realized volatility in the time interval, capital T1, capital T2, that we will see can be connected to the quadratic variation. So it can be connected to the sum of j running from 0 to m minus 1 of this log return squared. Yeah, the square log return. So we will write this out, the square log return. We need to square this. You can imagine we need to square this expression. Sum them up over all j's or over all i's. So I'll make an I of it in the slides and in the slides that I will post. And we will square it and we will look in detail. And you can imagine that the quadratic variation will play a role, and maybe also the other variations that we have seen. So let's write it out. We have to square this term. So this term squared will be sigma squared times this increment squared. It will be plus 2 times the cross term plus this second term squared. So we do that on the next page. The sum I runs from 0 to m minus 1 of log sti plus 1 divided by sti squared is then, as I mentioned, the sum I runs from 0 to m minus 1, sigma square w at ti plus 1 minus w at ti squared, plus 2 times the cross term, sigma times alpha minus 1/2 sigma square, the Wiener increment, so the increment in Brownian motion, wti plus 1 minus wti, times the other term, ti plus 1 minus ti, plus the last term squared, and then I think I should have a square here as well, alpha minus 1/2 sigma squared times ti plus 1 minus ti squared. And now again, we will look at a partition for which the mesh is small. So we have a fine mesh, T0, T1, etc. We will have many grid points and the mesh size in between is small. And then if we look at this, we take limit for the mesh width going to 0 and the number of points to infinity, then we will see that this one, it goes with dw, and dw is equal to the length of the time interval. So that is T2 minus T1. The second term here, when the mesh width is small, the second term, that is in fact the cross variation, dw dt. And we have seen that the cross variation is equal to 0. So that one cancels out. And the third term, dt dt, that was also set equal to 0. So these two will cancel out in the limit for small mesh width. So in total, this sum, the sum of log returns squared, that is equal to sigma square times the length of the time interval T2 minus T1. And in total, we see that we can estimate sigma square. We can estimate sigma square by dividing left and right hand side by this expression T2 minus T1. Sigma square can be approximated by 1 over T2 minus T1 times the sum of these log returns squared. So we can look at the intermediate time instances to the stock prices. We can divide one over from the other, and we take the log, we square it, we divide it by the length of the time interval, and we get an estimate for sigma. Yeah, the averaged or realized volatility, the average quadratic variation over the interval T2, T1. So that is a nice example of quadratic variation. And that concludes this part. So we will move on to section 3.5. And that is about Markov processes, but we will start with some repetitions. Some bases that we may need, and even more so, we will first discuss a theorem from 3.6 before we actually discuss the Markov process and the Markov property. So again, remember, let Wt be a Brownian motion, t greater or equal to 0. Now recall from last lesson that the filtration, Ft, t greater or equal to 0, it's a filtration because we know that if S is less than T, then Fs is contained in Ft. So it is information is accumulated. Yes, so it's a filtration if, first of all, Wt is Ft measurable. So, which means that Wt for t greater or equal to 0 is adapted to the filtration for all time t greater or equal to 0. And moreover, if S is less than T, then Wt minus Ws the information in the interval from S to T, that is independent, in fact, of Fs. Yes, so we have again these two notions, the increment being independent from the knowledge that we have gathered up to time S. Now, constructing a filtration, given the Brownian motion, well, for example, if we have the filtration Ft defined to be the sigma algebra Ws, where S is less or equal to T, then Ft for T greater equal to 0, that is a filtration for the Brownian motion. Yeah, it is measurable, and also again, in this case, we have the independence of the increment Wt minus Ws being independent of the information of Ws, or the information gathered up to time S. So we have proved earlier that if the filtration Ft for T greater equal to 0, when this is indeed a filtration for the Brownian motion, then Wt, T greater equal to 0, is in fact a martingale with respect to this filtration. It is measurable, first of all, because we know everything regarding this filtration. It is Ft measurable. That is one of the aspects for martingality. And the other one is, of course, that for S less than T, we should have that the expected value of Wt, given the filtration up to time Ts, up to time S, is in fact Ws. And this is the standard way of proving it. We add and subtract Ws from Wt, and one part is adapted to the filtration, is Fs measurable. One part is Fs measurable, and the other part is independent of Fs. Yeah, and the other part is independent of Fs. The part that is independent of Fs, that is just a regular expectation of the increment, which is equal to 0. And the part which is Fs measurable is Ws. And because it is measurable, we can take it out of the expectation operator, and we end up just with Ws. If you forgotten about this, look back at the previous lecture or look in the book where it's discussed in detail in section 3.3. Now we go to this 3.6.1, because what I want to do here is I would like to define a new martingale based on this T Brownian motion. I'd like to define a new martingale. And this is quite a nice exercise. So I hope you enjoy it as much as I do. Suppose we have this Brownian motion, Wt, T greater equal to 0. And we have script Ft, T greater equal to 0 to be the filtration for the Brownian motion. And we have a sigma positive. So we have again a volatility parameter, if you wish, which is positive. Now let's define a new stochastic variable, z of t, and it is defined like the exponential function of sigma w minus 1/2 sigma squared times t. So we recognize a geometric Brownian motion, but we also see that alpha is equal to 0 here. The alpha from before, alpha is equal to 0. So that is still quite crucial in this respect. So it is a special geometric Brownian motion with alpha equal to 0. Yes. Now, then again, if we look at the exponent, we see the same as before, but now with alpha equal to 0, we see that the exponent is in fact normally distributed with mean minus 1/2 sigma squared times t, and with variance sigma squared times t. forgotten this. I'll check it later. Now, what we can prove in theorem 3.6.1 is that ZT, t greater equal to 0, is in fact a martingale under the filtration. Well, first of all, it's FT measurable. So the knowledge is up to time t. So it's all measurable up to time t. It's FT measurable. That is one of the aspects that we should verify. And the second one is, of course, the important condition for martingales is this expectation of WT under a filtration up a knowledge level up to time S. That should be equal to ZS. So we should have the fact that the expected value of ZT given Fs is in fact ZS. This first one is repeated here on the slide. So this is the process we're dealing with. It's FT measurable. It is adapted to the filtration. Secondly, so we look at the expected value of ZT given script Fs, where S is less than T. And again, let's write it out. Well, first of all, we just repeat it. It's the expected value of this term. And we play our trick, the trick that we always play. We add and subtract sigma times Ws. Yeah, we add and subtract sigma times Ws. We always like to be in normally distributed variables, so we look at increments. We always go for increments here. So if we subtract sigma times Ws, we have this sigma times Wt minus Ws, and some part remains. So we write it out, and we see that we have this expectation of the e to the power sigma Wt minus Ws. Then this part here, that is just a constant, e to the power minus 1/2 sigma squared times t. This term is just a constant, so we can take it out of the expectation operator. It's over here. And the plus part is remaining, so that is here added, multiplied, so we know the rules of exponential functions, times e to the power sigma Ws. Now, how to continue with this? Next step. Next step is that also Ws and e to the power Ws is Fs measurable. So take out what you know. We know this. It is just e to the power sigma Ws. So we can take it out of the expectation operator. So it appears here, right? And what remains is this e, the expectation of e to the power sigma times this increment in the exponent. What to do with this one? Well, that is sort of interesting, right? It is e to the power sigma Wt minus Ws. And there the expectation. Now, if we look carefully at this expression, then we may recognize that we have seen these type of things before. Maybe in a little bit different setting, but this can be cast into a form that is connected to the moment generating function. Now we had the moment generating function, expected value of e to the power u times x. Now, if for x we look at our increment, so normally distributed, and for u we may look at sigma, then we see in fact that we can use known things, particularly because this is normally distributed. We can use the inside of the closed formula for the moment generating function in order to deal with this part. And this moment generating function, I have it here. Yeah, I have it here. in the next slide, remember that this increment Wt minus Ws is normally distributed with mean zero and variance T minus S. And then we have derived that the moment generating function is given as follows. It was written as phi with as subscript the stochastic variable, so the process Wt minus Ws, and as argument u. That is then by definition the expected value of e to the power u times the stochastic variable, u times Wt minus Ws as the exponent here. And we have seen that when this is normally distributed, we end up with this is e to the power 1/2 u square t minus s. Yeah. So x is normally distributed. More generally, when x is normally distributed with mean zero and some variance sigma square, then the moment generating function is e to the power 1/2 u squared sigma square. Now this is a little bit confusing because for the sigma here, we will end up with t minus s. And for the u here, we may end up with sigma from the previous page, right? So that's a little confusing, but you understand the meaning. We recognize this, we can cast it into the formulation of a moment generating function. We use the appropriate value for u. We know that this is normally distributed, and we know that the variance ends up here in the exponent. So we go back one slide, and we process this here. So we process this here. This was already taken out. So this is e to the power minus 1/2 sigma square t plus sigma ws times the result from the moment generating function is e to the power 1/2 sigma square t minus s. And here we see that some part cancels out. You see e to the power minus 1/2 sigma squared times t. And here we have e to the power plus 1/2 sigma squared times t. So they will cancel each other out. And what remains is indeed e to the power sigma ws minus 1/2 sigma squared times s. And if we look carefully at this and we compare it to z, then we see that this is nothing but zs. And that is exactly what we needed to prove, right? In expectation, the conditional expectation of zt given fs is equal to zs. So indeed, zt, t greater equal to 0, is in fact a martingale with respect to the filtration ft, t greater equal to 0. So that is sort of nice, right? So with the alpha equals 0, we have a martingale here, and we can prove that just by the standard techniques, essentially. And looking carefully, combining things, combining our notion of the moment generating function, combining our notion of the moment generating function with all the things that we knew before. Now let's look at the Markov property of a Brownian motion. And this is as follows. Let Wt, t greater equal to 0, let that be a Brownian motion. And let f script ft, t greater equal to 0, be a filtration for the Brownian motion. And then remember that this means that wft means in fact that wt minus ws is independent of ft, right? That is how we always see this. Now we have seen before that Wt is in fact a martingale with respect to the filtration. And now we show that Wt is a Markov process. And for this, remember from a couple of lectures ago, for this we use the independence lemma. Yeah. So the Markov process, remember what it means. It means that the expected value of a function of Wt given the information up to time s is in fact another function g of the Brownian motion at time s. So it is not the martingale condition, because there we don't have an f and a g. It's a bit stronger, in fact. So it's not a martingale. We have an f here, a function of wt, and that can be written as a function of ws. So it is a bit stronger. So let 0 be less equal to s less equal to t, and f a Borel measurable function. Then we look for a Borel measurable function g such that this holds true. Then we have a Markov process. Remember from the definition from a few lectures back. And in fact, we can construct that g. And that is done with that independence lemma, as I just mentioned. So for this, in order to construct this, we use the independence lemma, and that was in the book 3.2.4. Let calligraph G be a subsigma algebra contained in F, a subsigma algebra. And so we will first discuss this for two random variables, capital X and capital Y, two random variables on the probability space omega fp, such that xs of x, such that x is G measurable and capital Y, process Y, is independent of G. Then for any Borel function f, we have the following. So the properties of this conditional expectation. So the expectation of f, which is a function of x and y given G, is in fact G of x. Yeah. Where G of x, and in this case it's a running variable, so we make it a small x, where G of x is nothing but the expected value of f given as running variable x, little x, and y we keep as the capital Y. So let's construct this. Let's go back to Brownian motion and let's try to construct this. So let's consider this expectation that we are looking for in detail. So the expectation of f, which is a function of wt, given the filtration at s. And what we do as usual, and we do it here within the function f, we add and we subtract ws. So we have, this is nothing but the expected value of f with as argument wt minus ws plus ws. So we have done nothing in particular. We have just subtracted and added the same quantity. But now we have a part which is independent of fs, being the first part, and we have an fs measurable part, being the second part. So now we can use our tricks and techniques to take it from here. So by the independence lemma tells us that this should be equal to some g of g which only depends on ws, and that would show the Markov property. Yeah, and in this case, so this part is independent of fs, and this part is fs measurable. So we write g as a function of the measurable part. G of little x is then the expectation of this first part, f, which depends on wt minus ws, plus x. And I should have a bracket here, and I will do that in the slides. Now we can write this out, but because we know for this part, we know that this is in fact normally distributed. Recall that wt minus ws is in fact normally distributed with mean 0 and variance t minus s. So we can benefit from that. This is an expected value of some function, And that, an expected value of some function, and that is by definition the integral from minus infinity to infinity of this function. And we write that as f y plus x. So this function here we call y, times the probability density function of y. And that is the probability density function that we have derived earlier for the standard normally distributed random variable for the standard normal distribution with mean 0 and variance t minus s. So that was in fact 1 over the square root of 2 pi times t minus s times e to the power minus 1/2 y squared divided by t minus s dy. So what we did here, if we look back, what we did here, we say the independence lemma tells us that this should be a function of ws. And we know that this part is normally distributed. So we write this as an expectation is an integral of that function times the probability density function is the integral from minus infinity to infinity of this function, where y represents the standard normally distributed random variable, and x is that part which is fs measurable. Yeah. So we end up with this form for g of x. Let's write this out. Let's write this any further. Yeah. So again, by the independence lemma, we said g of x is the expected value of f of x plus this increment. And again, this increment is normally distributed. And that gives us the integral from the last page, the integral from minus infinity to infinity of x of y plus x, 1 over the square root of 2 pi t minus s, e to the power minus 1/2 y squared over t minus s dy. And again, in order to work out that function g of x any further, we would like to see that this function is in fact a function which only depends on ws, because that is the basis for the Markov property. We do a change of variables. Let u be x plus y, and then du is equal to dy, right? So g of x is then, this we just take out of the integral because it's a constant for that, 1 over the square root of 2 pi t minus s. And then what we get after the change of variables is the integral of u from minus infinity to infinity, fu, because this is the substitution, e to the power minus 1/2 u minus x squared. See, we replace y by u minus x squared over t minus s du. And now if we substitute back for x ws, as we had it before, then we end up with g of ws being 1 over this square root term, the integral from minus infinity to infinity, fu e to the power minus 1/2 u minus ws squared over t minus s du. So we're almost there. What we see here, namely, what we see here is we see an expectation. We see an expectation of f u here. So let's look at the next page. Yeah, what we see here is that this second part here, this part here, together with this, for this, we recognize a transitional probability density. In fact, we recognize a transitional probability density. We call it P. We give it arguments R, X, and Y. And that is in fact 1 over the square root of 2 pi R, e to the power minus 1/2 y minus x squared over r. And if we use this notation, if we adopt this notation, then our g from the previous page, with x being ws, r being t minus s, gives us, and y being u, right? That gives us that g of ws is the integral from minus infinity to infinity, f of u, a function f of u, times p with arguments t minus s, ws, and u, du. And this p here is known as the transition density. Starting at ws, going to u in time step t minus s. And this function here, where the running variable over the integral is the u, this function is seen as g of ws. That is the function of ws that we need in order to confirm that w satisfies the Markov property, that it is in fact a Markov process. And that concludes the lesson of today. I thank you for attention and hope to see you next time.